This video is going to be short, but highly mathematical. It's actually using vector calculus, so spherical coordinates get involved and it's kind of messy. So I'll go slowly and maybe even I can follow what I'm talking about. R, theta, and phi are the three coordinates that make up a position on the sphere. If you have all of these values, then that's going to locate a certain point. R will point out, theta will point south along like a longitude line on this sphere with the z-axis going through the North Pole. Phi will be pointing west like a latitude line. So here are our little infinitesimal changes. Small change in R, or the differential R, differential theta with a compensation value of 1 over R. Because as the R gets greater, the movement on the arc gets greater. So we have to compensate for that. For phi, this thing that's pointing west along a latitude line, we have to compensate for it with R, but also the sine of theta, because that little circle that it's going to make, or that latitude line that it's going to make, is going to be take more distance depending on what the sine is. If the sine is pi over 2, then all of the R. If it's not pi over 2, then it's going to take something less than that. Here's the gradient. The gradient is the rate of change of those three spherical coordinate axes. Here's the f is just a function. This is the r part of it, or the radial part of it. This is the theta part of it, and this is the phi part of it. The radial part, we don't have to do any fancy stuff here. It's just the first partial of the function with respect to r. As far as theta goes, see, we incorporate that 1 over r times the first partial derivative of the function with respect to theta, and finally the compensation factor is 1 over r sine theta, first partial of the function with respect to phi. This one seems relatively easy. It doesn't get too complicated. But now look at what we're doing. Now we're saying that we're talking about this is actually going to be the divergence of this A vector. Divergence of the A vector. Well, the vector is not going to be x, y, and z. It's going to be A radius, A theta, and A phi. This is the challenge, to see how this thing all plays out. And then we'll take it one step more and we'll have the Laplacian. Where in the heck did r squared sine theta come from? This is the unit volume in spherical coordinates. And just to review, it's shown right here. Change in r doesn't have any compensation factor. Change in theta has a 1 over radius compensation factor. And change in phi, which is the rotational, has a compensation factor of 1 over r sine theta. So essentially we need that entire compensation factor when we're talking about the entire volume over which we're discussing this. The vector is what we say, what is the divergence of the vector with respect to the volume? Divergence with respect to the volume. And here's the volume, here's the volume, here's the volume. And each one of those is multiplied by the vector factor. Now notice with respect to r, the volume the change in the volume has no stretching, if you want to call it that, has no stretching component to it. This one has a stretching component of it over r, and this one has a stretching component due to r sine theta. On to the Laplacian. What we're going to do is take the divergence now, not of a vector, but of the divergence of the function, which the divergence function is a, let me get the cursor set up straightly, the divergence function is a vector in itself. It has the three spherical components to it. So just like the vector, in place of the vector components, we have the partial with respect to f, which is the radial component of the divergence, the theta component of the divergence, and the phi component of the divergence. So maybe this helps make that not so screwed up or messy. Now let's break each of these into the separate components, and I'll multiply through the r squared sine theta. Here's the r component. Pretty simple. Where did the sine theta go? Well, sine theta in the denominator, sine theta in the numerator, and let's see, 1 over r squared, and then here's the r squared. So that's how that all took place. So the r squared doesn't cancel out because look, this is inside the first partial derivative. Now let's go on to the theta component. Now the theta component is going to take this line and this line to work out. Here's the theta component. Does anything simplify? Does anything simplify? Well, it looks like this r simplifies a little bit. That can be factored out. So let's see what happens here. Okay, there went the r factored out. Now let's see, I guess that's really all. Let's see what else can we do to straighten it out. I don't think there's any difference between this line and this line. So I'm not sure why that's on the page. I wrote it, but I'm not sure why it's on the page that way. Anyway, now for the phi, excuse me, now for the phi component. Okay, let's see, why is this just an r? Well, I'll tell you why. Because inside this thing is the 1 over r sine, so r sine cancels out an r sine here, leaving only an r. Thought that one would be the most complicated, but it actually simplifies better. Then we have, let's see, okay, just dr over d phi plus second partial of f with respect to phi. Oh, and where did the first partial of r go with respect to phi? Well, how much does the radius change when you change phi? It doesn't change one bit. So this thing actually becomes 0, and here's our result, nice and clean. Now to wrap all this stuff up, let me push this up, and here's our Laplacian. And we're done.